universe in which fundamental particles are not point-like, but they are extended objects. Now, there can be many kinds of extended objects. For example, one example is you can have, instead of having a point particle, which is zero-dimensional, you can have something which is one-dimensional, which is like a circle, or a string, or a loop, or a rubber band, basically. Or you can have an extended object which is higher dimensional. A sphere, for example, is two-dimensional. So an extended object can be like a sphere, for example, or even higher than that. But for this purpose of this talk, we will talk about extended objects which are like loops or rubber bands, like a circle. And so the question would be, how do you deal with it? And I will give a little bit, just tiny bit of how you deal with it versus how you deal with it with the point particles. So basically, we have structures atoms and nucleus we understand quite well. So everything is made up of molecules, and molecules are made up of atoms. Atoms have two, let's say, parts. One is the nucleus, which is at the center of the atom, and electrons revolve around this nucleus. The nucleus contains two different kinds of particles, protons and neutrons. But protons and neutrons are not fundamental particles, they are made in turn of other particles. Is there a pointer I can use? So protons and neutrons are further made up of quarks. And quarks come in different kinds of flavors and colors. So quarks come in 6 flavors and 3 pointer. I know there's pointer. So as you can see, the protons and the neutrons are, so this proton is made up of 3 quarks. So a proton is made up of an up-up-down quark. And the neutron is made up of an up-down-down quark. And other fundamental particles are, you can make other combination of these quarks and make other particles out of that. But this is the basic structure. But at the moment, our understanding is that the quarks are fundamental in the sense that they are not made up of anything else, just like the electron. And so the question, one question one can ask is, what if they look like point particles only because we are looking at them from very far away? So for example, if I have a penny over here, if I look at a point, small point, then the people who get some go, they can see the structure of the point. They can see the picture around it or make some estimate of the size of the point. But people in the back, or people, for example, someone very, very far away looking at this, it will look like a point particle. It will look nothing more than a point particle. They will see the very high, and you can throw very small sizes where And we are very fast that the particles in space going from the lower black dot to the upper black dot. And this path is represented by the blockade solid line. So suppose when we actually look at it, particle takes only one trajectory going from one part to the other. If you throw a ball, it will not go through like this. It will take a particular trajectory you can calculate. So the question that I raise as to how the particles will go from one point to the other. And this is of course determined by the principle of least action. This is determined by the principle of least action. The principle of least action indicates that a particle will take this path, will take the path which minimizes the distance between it. And so if I call small incremental distance df, then the total distance can be written as an integral of this from this point A to this point B. And then of course I can write it in this place, and this object over there is called an advancement. This is what the physics mostly works. And your classical mechanics course is an advancement for some particle of this kind of distance of the kinetic and the potential. Is half a meter squared minus here. And now to try to minimize this distance, that's the calculation of the solution. We investigate the motion that m that double dot is equal to minus e sine. So this comes from a simple principle that all we need to do is to minimize the distance. Let's say that some value of the distance. This is not the distance. Follow the path of least action. This thing is called the action. Follow the path of least action, and particle follows that path. The same thing is true for the string, but with slight subtlety, and of course there is more structure, so we have to understand this a little bit better. Remember that a point particle has no structure. So if I want to specify the point particle uniquely, how will I do it? Well, all I can tell you is I can tell you, here is the point particle. It's sitting over here. I give you its position, and I'm done. I have completely specified it. Or if it is moving, I tell you its speed at any given instant, and its position at any given instant, and I'm done. But for a string, things are slightly more involved. So here is a string. Here are two strings coming in. This is the time direction. Here is one vibrating string. Here is another vibrating string. They are moving in time until they collide with each other, and they form a one bigger vibrating string. So here is how you deal with the analog of principle of least action. That's how you deal with it. Here is a string at time tau A, and here is a string at time tau B. We fix these times, and now of course to fix the string, I need more structure because the string can vibrate. So I tell you what this string looks like. You know, it's a circle basically, but topologically it's a circle, but it could be some deformed circle like that as well. So I tell you what it looks like initially, at the initial time, and I tell you what it looks like at the final time. And I say to the string, now move. The string moves from this initial configuration in some way to this final configuration. But how does it
it move? What does it look like at any given instant? That is again determined by the principle of least action. So I can tell you here, the string moves in such a way that the total area is minimized. Rather than total distance now, it's the total area which is minimized. So for example, we know the string will go from here to here, but it can't go, like the string cannot just become too large at this point as it moves, or become too small at this point as it moves, because that will increase the area, total area. So this thing is called the world sheet. It's like a, topologically it looks like a cylinder. It's a deformed cylinder basically. And if I can calculate the area of this cylinder, I can do this by integration. Here's a small area element. I can integrate it from the initial to the final position. N over sigma, which is the spatial coordinate. This will give me the total area. And I just need to find a configuration which minimizes this total area. Now, the interesting thing happens over here, because that's where some of the power of string theory comes in, which is that one can show that the configuration that is going to minimize this total area will be represented by a holomorphic function. So in complex analysis, you must have heard of functions of z and z bar. Generically, a function can be, so if I have x can be written as z plus z bar over 2. So it's a function of both z and z bar. So we are looking for functions which are only functions of one variable, either z or z bar. If it's only a function of z, then it's a holomorphic function, roughly speaking. And if it's a function of z bar, then it is an anti-holomorphic function. So here, this worldsheet is going to have a minimum area if it can be represented with a holomorphic function. And that's one of the reasons of that power of string theory comes in, because we can now use complex analysis and all the properties of holomorphic functions, all this develops, which are very interesting special properties to actually work with that. So essentially, basically, this is how you start off with. So if you want to learn string theory, there are some standard textbooks that you can go. The most famous one still, I think, is the one which was written in the 80s by Green, Schwartz, and Whittle. And you go to, there are 2 volumes of that book. You go to volume 1, it starts off with some general discussion, and then it starts saying, let's work with strings. And this is what they do. They write down the area, they integrate it, they got this action, they vary it, get the idle and branch equations, which is the classical equations of motion of the string. Then they go to get other higher, more complicated things like quantizing this theory and so forth. But this is basically how you start off doing string theory. So, but what are the consequences? I will not go through the details of quantization and equations of motion, but what are some of the consequences of this thing? Well, one thing is, classically, strings can move in any space, any dimensional space. There's no problem with that. But if you want strings to obey the principles of quantum mechanics, then strings cannot propagate in any space. There are restrictions on where the strings can propagate. And for example, strings can only live in 26 dimensions. That's where the higher dimensional things come in. If you make strings go in lower dimensions, then some of the things that we want to be true, quantum mechanically, are not true anymore. So, principles of quantum mechanics essentially force the strings to live in 26 dimensions. Of course, 26 is too high. We are living in 4 dimensions, so 26 is too high. That's what people thought at that time as well. But what they said, okay, we can do something else. We can require that the strings satisfy some symmetry principles. And one of the principles was the supersymmetry. And if you require that strings satisfy supersymmetry together with principles of quantum mechanics, then it turns out that the strings can only live in 10 dimensions. That's still too large. The other thing very different, and this is the deep thing I will go into more detail in the next slides, is that strings see space very differently than point particles. The example I will show you will show that strings do not distinguish between, in some sense, the very small and the very large. They see it in the same way. So I will make this very precise in a minute. So this is the property of string theory called T-duality. And this is the one I'm going to go a little bit more detail. So the idea basically is the world is four-dimensional, but strings can only live in 10 dimensions. So the only hope for the strings to describe our world is that somehow the extra 4 dimensions are somehow not visible to us. And that's basically the idea that we can actually do compactification and wrap up these 6 extra dimensions to be very, very small. For example, the compactification is basically this idea. If you look at this pen, this pen is a cylinder. Okay? It's a solid cylinder, but suppose it's a hollow from inside, so it's a cylinder. Right? So it's 2-dimensional. It has length and it has a certain width in this direction. So this is 2-dimensional. The surface of the cylinder is 2-dimensional. You need 2 coordinates to describe it. One coordinate goes this way, which would be the x-axis. The other one is the periodic coordinate, theta. So the surface of this cylinder is 2-dimensional. But to those looking, again, this is the same idea. To those who are nearby, this does look like 2-dimensional. They can see the width. But for someone who's sitting at the back, the width is not that clear. It looks essentially like 1-dimensional. If you go even further, it will look like exactly like 1-dimensional. Only if you come closer, it will look like 2-dimensional. So this is a basic idea that extra dimensions are like this compact circle. They are very small. Of course, I can make this, I can make the radius of this circle large, and then even people in the back will be able to see that this is a large cylinder. But if the radius of this is very, 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 very small, then people in the back or even people in the front will not be able to distinguish it from just essentially a line. So this is the basic idea that somehow the extra dimensions that we have are very, very small. You can think of them as very small circles. And that's why people in 10 years ago, 15 years ago, were doing lots of experiments at CERN and other colliders, trying to figure out whether we can see those dimensions or not. Well, how do you see those dimensions? Well, take this, think of this as small, so think of this as very long. Suppose there is a person, a small tiny ball, a small tiny ant, moving from that direction, and a small tiny ant moving from that direction, coming very, very fast, and they collide. What will happen? Or rather than ants, let's do this very tiny balls. If they collide, what will happen? Well, 2 things can happen. The balls can collide like this, and then they can move off like that in the same direction. Or it could happen that they can collide, and then one of them can move in the other direction. It can follow this other direction. And if it follows the other direction, if I'm a 1-dimensional being, I can only look at 1 dimension. What will I see? I will see 2 balls colliding, and then one of them disappearing. That'll be like magic, basically. So what will I see? I will see kinetic energy plus kinetic energy. Energy conserved, 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 until the collision. And then not conserved at all. I only see half of it. So this is what they were trying to do in the colliders. They were colliding the particles and trying to see if some of those particles go off in those extra dimensions. And if they do, then there will be some missing energy. And they will be able to see that this missing energy is a signature of those extra dimensions. So this is basically the idea that extra dimensions are very, very small. So let's go into detail a little bit. So here is a straight line. So I will not do 6 dimensions because I can't draw 6 dimensions. I will just do 1. And the rest of them can be followed up in the same way. So here's a straight line. It's the x-axis. You can we have been working for it for a while. So now I do the following. At a distance 2 pi r, I put marks. So for example, suppose this was 0. So this is 2 pi r. This is 2 multiplied by 2 pi r. 3 multiplied by 2 pi r, 4 multiplied by 2 pi r, 5 multiplied by 2 pi r, and this is minus 2 pi r, minus 2 into 2 pi r, minus 3 into 2 pi r, and so on. So each of these marks is at a distance 2 pi r from each other. And now I do the following. Imagine, however you want to imagine, all these points, all these tick marks, is actually a single point. So this is like saying, I take a very long thread, I put tick marks on that thread, equal to 2 pi r, where 2 pi r is the circumference of this pen, and then I take that thread and wrap it over it. All the tick marks, because they are 2 pi r distance apart, they will become a single point on the circle of this cylinder. That's called compactification. We have taken the real line and compactified it to a circle. So a person moving on this real line will start from this point, say, and when he reaches here, he is back over here. That's circle. A person who starts off at this point moves here, and then when he reaches this point, he's back over here. Because when the tick marks are identified, this point is identified with this. Any 2 points which are a distance 2 pi r apart are identified to be the same point on the circle. So any 2 points which are whose difference is 2 pi capital R times an integer is actually the same point. So people, for the math people, this is R modded out by the group. R is a group, 2 pi R Z is a group, and you are looking at the quotient of the two spaces. So now consider a particle which is moving on this. Now you can think of it either as a real line with tick marks identified, or you can think of it essentially as a circle. So now if a particle is moving on this circle, the position of the particle is, let's say, denoted by x. But if the particle is at x, the particle is obviously at x plus 2 pi r as well.